So yeah, my name is Sayak Datta, and I'll be talking about that how tidal heating can be used to distinguish between black holes and any other things that is not a black hole. So I will start with some introduction. Everyone here is aware that GWs are being observed, and they're obviously the ripples in space-time. And several kinds of sources can emit gravitational wave. However, we will focus mainly on binary coalescence. And already with LIGO Virgo, we have observed hundreds of the order of 100 binaries already. In my talk, I will primarily focus on two kinds of binaries. One is extreme mass ratio in spirals, where the masses of the components of the binaries are too different, and also the comparable mass when the masses are nearby, equal to each other. And I think most of you are actually aware that the binaries are nothing but when two compact objects are rotating around each other, emitting gravitational wave. As a result, they are emitting energy, and because of that, they inspiral towards each other and finally merge. So in this context, there used to be thought about the detectors that we already have. Those are the LIGO detectors. But also these ground-based LIGO detectors are being upgraded, but as well as new ground-based detectors such as Cosmic Explorer, Einstein telescopes are upcoming. And also space-based telescope like LISA are also going to be launched in 34, I think. So these detectors will be observing gravitational waves at different frequencies, for example, LISA in megahertz, as well as if you look at ETCE telescopes, they will be observing in the same band as LIGO, but with much more sensitivity. So this is a great opportunity. As Vito was already saying this, this opens up the opportunity that, yes, we can do test of GR. We can ask the question whether the compact objects that we are observing are indeed black holes, whether we can also test some quantum effects near these black holes if they are black hole at all. So to address this problem, there are several methods have been devised. For example, the quasi-normal modes of these systems after they merge, they can significantly deviate from classical black hole, and you can use that to test the black holeness, as well as echoes can arise, which Vito had already discussed. The spin-induced quadrupole and multiple moments of the systems can deviate from the black hole moments that can also be used to distinguish. As well as usually the compact objects we see or we expect, we assume that they satisfy reflection symmetry across the equatorial plane of that object. But if it is broken, then this can affect the orbital motion as well as the multipolar behavior. So that can also give us some clue, as well as the tidal deformability, which Tanya had discussed yesterday. They also can affect they can also have significant contribution, especially in LISA, where the extreme mass ratio in spirals will be observed, very small values of tidal deformability will be. But I will not talk about any of this today. Today's topic will be solely tidal heating. So I will come to what is tidal heating. Before that, I want to just motivate the situation a little bit more. So usually the black holes are defined by assumption or the theoretical motivation that their horizon, they have a horizon, and because of the causality, nothing can escape from the horizon, and they are the perfect observer. But if the black hole or if these compact objects don't have a horizon, or at least the horizon actually is modified in some sense, then this will lead to some imperfect absorption, and which can be mimicked by assuming some reflectivity. And therefore, if we can measure some reflectivity of these compact objects near the surface, that can be a signature of deviation from black hole paradigm. So we already had discussed about this, so I will not give too much time in this, but I will mention that tidal heating can indeed be used for this purpose. So what is tidal heating? So when there is a binary and the components are affecting each other, each component gets affected by the tidal field of the other component. And this And if these bodies have some kind of absorption capability, then this tidal field leads to some absorption phenomena going on. And as this originates from the orbital motion of the components, this energy there, this initiates an energy exchange between the orbit and the bodies. And this is called tidal heating. And as it affects the orbital motions, this affects the emitted gravitational wave. So observing the gravitational wave, we can probe this properties. The point is, a normal star, which is not a black hole, that case also tidal heating is present, but in that case, the absorption phenomena is associated with the viscosity in the material. But in case of black holes, what happens because of the perturbation, the black hole gets perturbed and the mass of the black hole changes, and that creates this absorption phenomena. It's not necessarily an increase. Even though I have written increase, that can be decrease also, but it's an exchange of the mass with the orbital energy, which creates tidal heating. Now, the interesting thing is that the mathematical expression for tidal heating of a star as well as of a black hole can be brought into a similar footing if you identify the viscosity of the black hole to its mass. Then you can compare the viscosity with neutron star. For neutron star, the viscosity is like 10 to the power 4, but for black hole, it is like 10 to the power 15. Roughly, you can say that the tidal heating is proportional to the viscosity. So you can say that the tidal heating for a black hole is way more stronger than neutron star. So for any practical purposes, tidal heating is primarily a very phenomena of like black hole-like object. And this is interesting not only because of we can test some other kind of objects, but also tidal heating can be used to distinguish between black hole and a neutron star because of this. As a result, this can give us understanding regarding the maximum mass of neutron star as well as the smallest mass of the black hole. This I will, if I have time, I will come later. So first, I will focus on the tidal heating in extreme mass ratio in spirals. So what are the extreme mass ratio in spirals? So here I am giving a schematic pictures. So usually the galaxy is expected to have a supermassive black hole like 10 to the power 5, 10 to the power 7 solar mass to be inside the galaxy. Now, if a stellar mass compact objects like 10 solar mass, 100 solar mass, something like that, gets captured around these supermassive objects in an orbital motion, then these systems are called extreme mass ratio in spiral. And these spirals will go on, they will emit gravitational waves, so on and so on. So practically, this is just like a point particle perturbing a black hole spacetime. So this can be tackled by normal perturbations of black hole. And for that purpose, the wild scalar psi4 actually is considered to take into account. And this wild scalar satisfies Tucholsky equation. So you can solve Tucholsky equation, find the psi4. Psi4 is very good because from psi4 you can get the GW waveform, energy fluxes at infinity, as well as at high. If you do all these things, you can construct the inspiral. And that is what I'm showing you in the plot here left, that with respect to time, how the radius of this orbit evolves. If you start from radius equal to 10 m, mass m is the mass of the supermassive body, and how much time it takes to reach the ISCO. So you can see, depending on the spin, it can take months to year. And note, these radial values are actually will be in the Lisa band. So we will observe these systems in Lisa band for almost months to year. So what happens to the waveform? How does it look? So to address that question, we construct two kinds of waveform, one which ignores tidal heating, another which takes account of it and calculates the waveform, and that is what I am plotting. Both of them are. So for spin 0.7, it looks like visually they are not too different, but note that in x-axis, it is just 1 month in time. That means we are somewhere here. So much time is left to go. But even in such early phases for spin 0.9, you can see there is a dephasing. That means the waveforms are getting shifted from each other, as well as the amplitudes are different. So effects are quite strong. So to properly giving an account of this dephasing, I'm plotting in the y-axis here the dephasing due to tidal heating in radians with respect to time. And you can see that the dephasing can grow to like 10 to the power 3, 10 to the power 4 radians, depending on the spin of the supermassive body. To give you even better quantification, in the right, I'm showing you a mismatch plot. So mismatch actually is you take two waveforms and calculate the mismatch between them. And this tells you how similar two waveforms are. So if the mismatch is 0, that means you can say the waveforms are very similar. If mismatch is 1, then you can say the waveform is completely different. And now we can see that the mismatch introduced by the tidal heating is very strong and can be very important in the context of MRI. But what if these compact objects are like something in between, it has some kind of reflectivity? In that case, the tidal heating flux of this body will get modified by the reflectivity of these objects, while they will be proportional to the black hole tidal heating. And there will be some ordered epsilon correction to the heating. And what is epsilon? The epsilon is defined by the surface position at which your reflectivity is defined. So in this case, it is considered these objects are almost as compact as black hole, but they are a little bit shifted outside of the black hole. So their surface position is slightly larger than the horizon position. So epsilon is a small one. This epsilon also affects the tidal heating. Now, if I only focus on the reflectivity for now, that the mismatch game I discussed earlier, you can do again now. You calculate the waveform, assuming some reflectivity, and calculate the mismatch. And you can see when the reflectivity is 1, that means tidal heating is absent. Mismatch is very strong, which is obvious. But also notice when reflectivity is of the order of 10 to the power minus 5, that can also have an observable impact, which is represented by the black dashed line. So this is very promising. But then I will ask the question whether they will be measurable. I have shown you that theoretically there is a significant contribution in the dephasing, but can they be measured? So to tackle that problem, we have defined a parameter called H, which has been multiplied only to the tidal heating flux of the black, which this H parameter you can think as like 1 minus reflectivity square. For obvious reason, we name them as horizon parameter. You can say that when H is equal to 1, this term contributes, so it is a black hole. So therefore, in the presence of horizon, when H is equal to 0, there is no horizon, and something in between will be somewhere in between. So we try to measure this parameter. So again, we consider H to be in the extreme association spiral, but the source we consider to have H equal to 0. That means it doesn't have a horizon. And we try to estimate the error in this parameter, in particular in this kind of source, with Fisher matrix. And you can see that the error can be of the order of 10 to the power minus 3, and actually it can go to 10 to the power minus 4. And this is consistent with our theoretical predictions. So that is very interesting. That means the reflectivity indeed will be observable. But I will jump now to the impact of the surface position. So this is the same schematic picture that I had discussed earlier. Here I'm showing this black cylinder as the black hole surface, the horizon, and this green surface is the shifted surface where the reflectivity is defined. Now, if this surface is shifted from the horizon by this epsilon, what properties can it have? If you assume that the outside metric is like curve, then you can calculate the area of this surface, and now therefore this area of this compact object can be expanded in a perturbative expansion of epsilon. Now again, therefore, just like black hole, this area will depend on the mass and angular momentum, but the rate of change of the area will be again a perturbative expansion of epsilon, where in epsilon going to 0 limit, this will give you the black hole. So this can be used to calculate the tidal heating of this object. Usually, how the tidal heating objects of the black holes are computed? This comes from that the rate of change of area of the black holes depends on some perturbation quantity psi 0. You calculate the psi 0 at the position of the horizon, so you know the rate of change of area of the black hole. Now, if you know psi 0, that means you know the rate of change of area, and therefore you know the rate of change of mass, and this actually gives you the tidal heating. So now you can continue this thing again for these compact objects, only you will calculate the changes at the position of reflective surface. And if you do all those things, then the rate of change of mass will have a term like T square, which arises from the reflectivity, you can think of as a horizon parameter. And there will be some perturbative expansion of epsilon. But the leading order term M0 is the black hole part, and M1 is the new part. So I am here actually showing you this flux, this DMDT. How does it look like? The black dashed curve here actually represents the black hole. And if you increase the reflectivity and epsilon, it actually becomes more positive and differs from black hole. But if you become a little bit too adventurous and take epsilon to the order of 0.1, then it can change the flux significantly in the sense that it can flip the sign of the black hole. That means that is very interesting. That means that not only the reflectivity, but also epsilon has very strong contribution in tidal heating. Now here I am plotting the leading order term M0 as well as the first term M1 here. The solid lines are the set which represents the leading order black hole term M0, and these dashed ones are the M1 terms. You can see even though they are different, their order of magnitude wise they are very similar. They are not too different. So therefore you can expect from this what kind of epsilon can be observed. In the DMDT, there are two terms. One is along with the leading order black hole term, there will be a term like M0 into reflectivity. Another term is like M1 into epsilon. Now, as M0 and M1 is of the similar order, therefore, whatever constant we are thinking of reflectivity can be thought for also epsilon. Therefore, I can safely say epsilon of the order of 10 to the power minus 5 can have significant imprint in the black hole, in the extreme mass ratio spiral. So now I will shift the gear and I will discuss the comparable mass ratio spiral. This was already discussed quite in detail by Shukanto yesterday, so I don't have much more to discuss, but still I will go through a little bit. So what is going to happen in comparable mass ratio in spiral? In comparable mass ratio in spiral, both of the body's tidal heating contribution will be significant. So you need two horizon parameters, H1 and H2. But when you calculate the tidal heating flux now, tidal heating phase now, you see that there will be two terms. One is coming from H1, another is coming from H2. This should have been 2, this typo. So those two parameters, H1 and H2, becomes degenerate. You cannot measure them separately. So what you can do, just like the spin measurements, you can define some effective parameters, HF5 and HF8. And in terms of them, the tidal heating tidal heating phase will look very simple. And you can try to measure these two parameters. Now, the point is, if you look at this purple region in these color bars, which represents the mass ratio, that the highest value or the larger values of this parameter represents actually the extreme mass ratio. And for low spin case, that means effective spin equal to 0, HF8 parameter is more important because it is not exactly 0, while HF5 is 0. So for low spin case, this parameter will be more important. So with that, we try to again estimate the error that we will observe in them. We had found that in LIGO-Virgo, their error will be quite high. But however, in ET and CE, their error will be very low. These are actually like less than 10% error, depending on the values of the parameters. HF5 and HF8, both of them are very well measurable. These are for 200 megaparsec, but in the right, if you go to even larger distance, the error is still low. So third generation has very good hope that lots of these things can be done with very good accuracy or maybe precision. While passing by, I will make just a comment which Shukanto also had discussed, that tidal heating can also be used to distinguish between black hole and neutron star. So here we do the study for LIGO-Virgo case and trying to see whether tidal heating can be used to distinguish between black hole and neutron star using Bayesian analysis. I will not go into the detail, but I will say whenever you see the red curve is shifted from the black curve, you can say, okay, in this region, black holes and neutron stars can be distinguished. So you can see in 1 to 2 solar mass, yes, they can be distinguished, but 2 to 5 solar mass, they cannot. This tells you that In 1 to 2 solar mass, tidal deformability actually contributes quite well. So this is why we are able to distinguish. But in this mass range where tidal deformability does not contribute and in only distinguisher is tidal heating, the result is bad. That means in LVK, using only tidal heating, it will be hard to distinguish them. But maybe in third gen, there is a very strong chance that it will be used. But we need to do the study to make a proper comment on that. So I will conclude this part here and I will move to the final part, which actually Vito already had discussed today. So maybe I would not have to talk too much about the basis of it. So it is about the impact of area quantization. So Vito actually discussed about how the area quantization can impact. So I am going you some details of it here. If you assume that the area of the black holes are indeed quantized by a parameter alpha and a capital N, which is an integer number, then as the mass, area, and angular momentum of the black holes are connected, therefore you can say that the mass of the black hole will also be quantized. So when there is an energy exchange, any kind of energy exchange with the black hole can allow only that kind of energy exchange, which is allowed by this quantization. So by assuming some leading order terms, this paper, Agullo plus, Vito was also co-author, they actually showed that this will imply that certain energy quanta will be only allowed to have this kind of transition, which implies that this will be certain value of frequency which will be allowed. So the leading order term is actually N alpha. Small n actually shows the ladder of the quantum transition, and omega h is actually the angular velocity of the horizon. So see here, there is no area quantization effect, but this term actually have area quantization effect. So you can see that only in these frequencies the black holes will be exchanging energy, and that is what is plotted here. That is what from this paper. Here the different frequency lines has been plotted along with the post-merger quasi-normal frequency. Along with this, they also calculate the gamma, the line width of this using the Hawking radiation. And we will use this gamma and the omega n for our purpose. Our context is actually tidal heating, but you notice till now that tidal heating also talks about this energy exchange. So therefore, whenever there is energy exchange is happening in tidal heating, it has to happen in such a manner so that this quantization omega n is respected. Therefore, in tidal heating case also, if the frequency satisfies, if the inspiral frequency satisfies these frequencies, only then tidal heating will contribute. Otherwise, tidal heating will be vanishing. That means the horizon parameter that we had defined earlier is now a frequency dependent thing. It is non-zero only in certain frequencies, that is the omega n, where it is 1. In other places, it is either exactly 0 or suppressed, but there will be some region because of the line width. And if you consider this horizon parameter, the frequency dependence now, and compute the tidal heating flux, the tidal heating flux will also be quantized now. So here actually I'm giving a schematic picture just to make the point. In the flux case, the point is flux will also be quantized because of that. And this is a quite distinct feature. But in the inspiral case, will these frequencies indeed be observed? So to stress the point, what I'm plotting here is the solid lines, that is black is for n equal to 0, the lowest frequency value, and other twos are n equal to 1, but for different alpha values. Along with that, dashed and dot lines are actually some contact frequency in the inspiral. Now, what is a contact frequency? The contact frequency, you can think the highest frequency in the inspiral when the two bodies are actually touching each other. Now you can see when the mass actually is equal, that is the dashed case, for most of the range, this contact frequency actually is lower than even the F0 and F1. That means in these ranges, below the contact frequency, there will be no tidal heating because lowest frequency allowed by the area quantization is actually above this. While if you go to a little bit higher mass ratio, then situation is better because then contact frequency is higher than the is these frequencies. But if you be a little bit more careful, then you can address the question that what about the ISCO? Because ISCO frequencies are actually lower than the contact frequencies. So here I'm showing you cases for extreme mass ratio, and I'm plotting the ISCO frequency in the purple and the black curves as the F naught. And you can see that above 0.36, the ISCO frequency always lower than this F naught. That means you cannot observe these F naughts before ISCO. But we have seen that below contact frequency, you can have something. So that's why we computed dephasing only because of this area quantization part and between ISCO frequency and a light ring. And in that case, you can see there is a dephasing between dephasing because of this quantum black hole contribution. But note, we are doing a stationary phase approximation, which is not exactly valid in this case, but it is just to prove the point. While if you look at the contribution with respect to the classical black hole, you can see it is quite low. That is understandable because in classical black hole, it will contribute everywhere, but in quantum black hole, it will not. So to move on, if I move on, I can conclude that if the mass ratio of the objects are like less than 0.34, then with respect to contact frequency, F0 is lower. Entire range of alpha, that is the area quantization parameter, is observable if you consider all kinds of detectors. Above spin 0.36, the tidal heating in extreme mass ratio in spiral up to ISCO will completely vanish. Therefore, if we can measure tidal heating that corresponds to classical black hole, that will completely rule out at least this kind of area quantization. As well as the line width gamma, which have been calculated from Hawking radiation, if we measure this gamma, we can have some understanding about the Hawking radiation from the observational perspective. So I will conclude. The summary is that in MRI, tidal heating is a very strong effect. So very small values of reflectivity can be observed. With Fisher analysis, we indeed suggest a similar thing. The position of the horizon surface, epsilon, is also very important in the context of tidal heating. In comparable mass ratio in spiral, you need some effective parameter, which will be well measured in third generation detectors. And area quantization can be ruled out or be probed with tidal heating. So I will stop here and take questions.